with number 6. Start from here. Okay, so number 6, if I recall correctly, you had some sort of drill bit thing. It had a diameter of 8 inches. I think I said that this is a this is an abrasive drill. So means that it cuts by rubbing essentially away at a rock face. So it cuts via shear stress. That shear is called we'll get to how that links in a minute. Probably does it by friction because I gave you a coefficient of friction of 0.05, I think. And I think there was a ultimate stress for the the cutting head, which was 540 megapascals. Okay. So we have an ultimate stress, 540 megapascals, and I think I said for a factor of safety of 10. So did I give any more information than this? Since you have the thing out.
I didn't.
Okay, fair enough.
The diamonds are half of the surface area.
Yes, that's kind of a big thing. Okay. So the actual bit of the head that cuts is 1/2 the head's area. Okay, and I ask for what is the force that's used, what would be the maximum force to advance the bit, right? Cool. So that'd be like a force pushing this way. Okay, so to advance the bit through the rock, that's what we're trying to find. Okay. So let's just kind of start from the beginning. If we're looking for the maximum, that means that we're going to be designing to whatever the ultimate stress is, taking into account the factor of safety. So this means that the stress that I'm designing to is not 540 megapascals, but it's actually what? Right. Because if I have a factor of safety of 10, I work my little equation here. So what? Sigma ultimate over sigma allowed equals factor of safety. For the most that I want to allow this head to see is 1 factor of safetieth, or in this case 1/10 of the ultimate strength, then I'm not designing to 540 megapascals. I'm designing to 54 megapascals. So that's kind of like step 1. Okay. So I have a stress. I want to get to a force, so it's logical that I need an area. So I can give myself a little bit more room. I know that I actually only care about like half of this. Not to scale. So do my pi d squared over 4 deal, and multiply that by 1/2. That gives me the area of my cutter, if you will. We all on board? Cool. All right. So that gets me to there, and area of that. I forgot my calculator today, but it's like what, 64 over 416, so like 8 pi, so like 24-ish, 25-ish square inches. We'll just kind of run with that number for right now. So that gives me the area. If I divide, this is tau, sorry. If I divide these two, I get a force. But that's not the force that I'm looking for yet. Because, so if I, okay, over a cutter. So I do that, I get a force, but because the stress that I'm starting from, which we've already said is a shear stress, because that's how this thing cuts. And hence it cuts by generating a shear stress. That means that this force is also a shear force. We know that shear forces act parallel to the faces that they generate stress on. So that means that this force is going like that. That is not the force that's advancing the bit. So we need to do one more thing. And we know that one really is called that, like how you make shear stresses a lot of the time is through friction. Because friction is a force that is by definition parallel to surfaces that are in contact with one another. It's generated by normal force and all of that. So I can use that to translate this shearing force into some sort of axial force that's pushing the drill bit along. So once I get the shearing force by multiplying my allowable stress by my cutter area, I can say, well, P equals, wow, here we go. Frictional force equals mu times the normal force. In this case, the normal force is the same as the force that's being used to advance the drill bit. So the force advancing the drill bit's the same as the frictional force divided by the coefficient of friction, given as 0.05, and it ends up being a ridiculously large number. It's like 1,000,000 something in pounds. Does this make sense? Any questions on any of this process? And help me out here to make my questions a little bit better. Did the phraseology make sense? Does this process make sense? Yes. So you can do either. This is kind of the trick with any kind of unit prefix. So how do I do this? Yeah, let's do that. So say that I have tau and it's in units of megapascals. So that's what a mega times a Newton per meter squared. All I really care about is newtons per meter squared. And when I multiply different things by it, like say I multiply this by an area, I'm just like canceling out that bit, right? So if you don't want to convert this into regular pascals, all you need to do is carry the mega. Or say that, what would be a good example? If I had tau and I divide by force in kilonewtons, that kilo is what you call a 10 to the third, right? This is like a 10 to the sixth. So you really just have to bookkeep your orders of magnitude. However you want to do it is up to you. If you want to convert everything to the same thing, like have everything in kilonewtons, kilopascals, because then they just cancel out, that's fine. If you want to go back to base units, that's fine. You just have to bookkeep well. And if it's called where I get a little, uh, yeah, and that's what it's called, and that's really the thing, just making sure that you keep track of them. Because yeah, if it just floats around, it's a problem. Yes.
So you have to convert between either pascals and PSI or...
Correct, because those are not in the same unit systems. Yes. You have to go between PSI and pascals. You can't mix metric and English. Yeah. Yep. Any other questions? All right. Cool. Then let us away. We'll hit up question 5 on Thursday. Because I don't want to get too far behind here. Okay, out of this one, into this one. Okie doke. So, if you remember last time, we talked a little bit about stress strain curves. We were looking at them as ways to investigate how materials react to strain, talking about a little bit about fair criteria, about what the proportional limit is, so as the limit on linear behavior, the so-called proportional limit, which is close to the yield strength, is kind of the end of where we can apply Hooke's law, in a sense, because you see the graph goes very nonlinear after that, and Hooke's law is a linear equation. So we're talking a little bit about that. The difference between the proportional limit and the yield strength being the definition of it's called what strain the material returns to when it's unloaded. If the material is still inside the proportional limit, then by Hooke's law, if strain is 0, stress should be 0, or vice versa. When the material is yielded, when stress is 0, strain is a very, very small number that is not 0. So we said 2% to 4%. Sorry, 0.2% to 0.4%. So 0.002 to 0.004. And that's kind of the yield strength. And that's, he said that that's important to us because something can yield without breaking, kind of like the axle on one of the intro to engineering trebuchets last semester. The thing was bent in a V, it wasn't broken, but it definitely it definitely yielded and you couldn't actually use it for what it was intended for, at least not very well. So that'd be an instance of why we'd want to care about yield strength before ultimate strength. So we care about down here instead of up here because of the physical implications for the material itself. So are we all on board with that? Sweet. Okay. So fun. So now so that's kind of how. So it's more about the curve, but what about if we see curves kind of stopping in different locations like this? What does that mean? Dang it, it's the one day I forgot to bring my examples. Okay, anyhow, so these two curves here are for two different kinds of material. If you think about, say, like a piece of glass, I am terrified about those, those lids that go onto like electric skillets. I'm terrified of the knobs because I tried to screw one of them back on, it had fallen off, and I'm just casually tightening down the nut that holds the thing on, and the thing just explodes in my hand without any kind of warning. That's an example of a brittle material. It's something where it will so it's called stress will build, stress will build, stress will build, but you won't really know that it's building that much because it's not straining by a whole lot, and it never really reaches a discernible yield point. Its yield strength is very, very close to its ultimate strength. So when it fails catastrophically. That's a brittle material. So this curve here would be something that you'd see for something that is quote unquote brittle. Kind of like peanut brittle actually is very brittle because crystallized sugar is a brittle is a brittle substance. The upshot is that there's not really a area of plastic deformation. It's pretty much an elastic region. So on a ductile material, that'd be anything before yield. Here too would be anything before yield. Essentially everything is elastic. And as soon as it starts to yield, the thing just goes. That's a brittle material. Trying to think of other examples. Some forms of very, very hardened steels, I think you could make the case are brittle. Some of them. The very, 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 very hard steels. Graphite in your pencils. Other examples: some kinds of plastics, especially 3D printed ones, based on how they cool, can be very brittle. But a lot of materials that you'll be working with are what we call ductile or ductile, if you choose not to pronounce since the I as in an exaggerated fashion as I do. And these essentially do have both an elastic and a plastic break region. The ultimate strength is fairly well displaced from the yields strength. And these are a little bit more common in our world, like wood might be something that you actually no, different kinds of wood you could call ductile. Aluminum is a ductile material. You can flex it back and forth, and it won't break for a relatively long time. Most steels are ductile materials. Most metals are, really. Do you just call does this kind of intuitively make sense? Okay, cool. And the difference in where their ultimate strength is with respect to their yield point is kind of the difference between these two kinds of materials. So the next question is, how do we figure this out? And the answer, which I was hoping might be a part of this class, and well, doesn't look like it, unfortunately, is typically something called a tensile test machine, which can look something like this. It's essentially just two grips of varying configurations, grabs onto some sort of test specimen or a coupon that is either screwed into the grips or clamped by them, and you stretch it. And if you do this for, say, a ductile material, I really wanted my samples for this. You'll see a break that looks like this. This is characteristic of ductile failure. So can someone kind of describe what they're seeing in this to me? If I look back at how the specimen was and how it is there, what changed between those two? got longer. True. Okay. So there was some form some form of elongation. What else? Yeah.
Pinched in the middle.
Pinched. So there's some diameter reduction or necking, not rubber necking. The usual kind of necking. Wow, I cannot write a K. Starts again. Promise that actually says necking. Anything else? Okay. And if you look at the broken specimen here, these faces aren't flat. They're a little rounded. These are all characteristics of a ductile failure. There's what's called appreciable strain. You see some sort of necking in the specimen. When it actually fails, the surfaces aren't flat. There's what's called, they're a little convex or concave, depending on which one that you're looking at. Also, you might wonder, what the crap is this? I mean, if it already yielded, why is the stress going up? And that's actually based on how the grains of the material reorder themselves in response to stress. I don't know, you guys have all had a geology course or in a geology course? Okay, so like rock is made out of grains, right? Like it's not one solid piece of material, it's a whole bunch of little tiny things. And it's the same thing with metals. So I'll have a micrograph later on. But based on how you work that material and how you stretch it, you strain it, those grains start to reorder themselves. They slip a little bit. They deform, and it changes the characteristics of the material, and you get a different stress-strain response. The elastic modulus, interestingly enough, stays the same, but the response of the material becomes different, if that makes sense. We cool with that? Actually, let me explain that a little bit more. So like, if I strain a material out to here, say, and then I stop and I release all the stress on it, it'll travel along a line that is defined by the elastic modulus. So just as in the proportional region, inside of the proportional limit, it'll respond according to Hooke's law. So kind of like sigma equals E epsilon. It'll respond like that there. In kind of the same way, it'll respond here. It'll just come back to a non-zero strain. So if you added in some y-intercept to that, it's still moving according to the elastic modulus of the material. It's just bouncing between different points. And this is because of the phenomenon known as strain hardening, reordering, realigning, and deforming those grains. Cool. All right. So that's ductile failure. Brittle failure. This is so cool. This is so cool to me. Brittle failure is interesting because the two surfaces are virtually flat. Like if you break a piece of glass, anyone here broke a piece of glass before? It's just me. Okay, so like it's called the edges of the piece of glass, the shards are all flat. And not just for like safety glass, for tempered glass and anything else too. The edges, even whatever shape that they're in, the faces are all flat. Like you could piece together the glass and it would look like the actual thing of glass because it hasn't really deformed all that much. There's no or virtually no necking or other kinds of deformation at the break. It's as if the two bits just kind of snapped off from one another. That's a brittle failure. Now, it would be difficult to call any given material brittle or ductile. Well, it can be. For example, this is a typical stress strain curve for like for concrete. Now, would you say that this is acting brittly or ductilely? And if you need to caveat your answer, feel free. Option C. Describe option C.
It looks like when it's getting stretched, it's more brittle, and then when it's compressed, it is ductile.
Okay, which way is being stretched again?
Up.
Okay, so this is in tension or being stretched. It's usually a positive stress. That means this is compression. And every now and again, you'll run into something like we have a compression test machine over in Sullivan 3. It lists compression as a positive stress because that's all you can do with it. So watch out for people who break your sign conventions. But yeah, Ian, you're absolutely right. It acts more like a brittle material in tension and more like a ductile material in compression. So you can have materials that exhibit characteristics of both, but it's not always true. That's not always true. There are some that are just decidedly ductile in both tension and compression. There's more of a there's more of an exercise that you can see more than one type of behavior. That's what I'm looking for in a single material, all based on how the grains of the material interact. So don't worry, you don't have to know how or why this occurs. Right now, it's just this can occur. Okay? Cool. Okay. Cool. Actually, we just talked about that. It's called one of the last things I wanted to touch on with stress strain curves is alloys. So these are all different ways that you can adjust iron. So does anyone know what steel is? Yes.
Carbon and iron?
Essentially. So steel is essentially if you take iron, which is relatively soft, and add different amounts of carbon to it, and do it under different temperatures and cool them at different rates and whatever, you can come up with all kinds of different steels, all of them with various strengths and characteristics and whatever. But what's kind of neat about them is, well, here, what's common to all these different alloys, all these different alloys of iron? They are all ductile, although that slowly decreases, right? Because this ultimate strength is slowly getting closer and closer to the yield point. But what's common about their pre-yield behavior? So before they yield, is there something that's kind of the same? Okay, slope. What's the slope above the stress strain curve before you yield?
Less.
Yes, the elastic modulus, modulus of elasticity, Young's modulus, whatever you want to call it. They all have virtually the same Young's modulus, which is interesting, right? So the point is even though each one has different ultimate strength, each one has different yield strength. All these different alloys of iron in this case share at least the same elastic modulus because of their common origins. So it's just another good thing to have in the back of your head. A lot of things that you'll get here are good rules of thumb that will be very, very useful. Cool. So this is just what I was talking about before. This is a microfilm of a piece of metal. Probably looks really similar to a rock, right? And this is what is the cause of all the strain, of the strain hardening that we were talking about before. Cool. Do I want to do that? I have 13 minutes. Do that or that. Okay. You know what? I was going to talk about thermal stress today. I might just do that on Thursday, and let's do the rest of let's just do problem 5 now. Give a little bit more time to work with it. Sound good to you guys? Cool. All right. Oh, I didn't put that at the end of my presentation. Okay. So I'm going to need someone to shout out some numbers for me. I know I got, so in problem 5 on the homework, I had a hanger, her block thing. This is attached to a ceiling. And I have a rod coming out of it. On each side. I think it specifies P over 2. Okay. Then I have some dimensions here. Okay. I think that's all. Is there any more information that I'm missing here? Do I have like an ultimate strength? I think I do. Okay, so I have like an ultimate strength of something, and that is what? 175? 175? 75. And I think there was a ultimate shear strength of the wood. 7? Great. Just for reference, we're given 2 different values for the wood because wood, like we talked about last week, is a composite material. So it's made up of more than one substance acting as one unit. And because of that, you end up with different strengths and stiffnesses based on what direction you're pulling from or what kind of stress you're talking about. Steel is not like that. It's one kind of homogeneous thing and acting the same no matter which way you push on it. So that's why we only have one strength for that. Okay, and then we have a bunch of dimensions and stuff too. But first things first. So we're given 3 different strengths. I think that the question is, find the maximum force that you can apply to this block, right? So that means that we need to find what all the limiting cases are, what all different ways, what all different kinds of stresses are being put onto this block and this pin, this metal pin. So, as far as we've gone, the pin is purely experiencing what kind of stress? Shear, right? You have a force coming down. If I took a cross section of the pin, the force is always going to be parallel to that cross section. So the pin is in pure shear. The block, though, is kind of a mix of everything, right? Which was called based. I can cut different cross sections and get different things. You could say you could make a cross section through the pin that goes this way, I guess. But would that have more or less stress on it than the cross section, what's called the cross section that we're already looking at, one that's vertical? Why would this cross section be of more interest than this one? Which one has, what's called, both of them have the same load, right? More or less. Which one has more, which one has less area? The one that sits vertically by a lot, right? I mean, yeah, it's a really, really long item. Therefore, there's a whole lot of cross-sectional area going this way, not a lot going this way. Therefore, which cross-section do we care about more? Say again? Right, so we care about it in shear more than in tension. So that's thing one. So we're not really going to care about the other one. We're just going to care about the shear case. Okay, so I have the pin and shear. Let's talk about the block. Try to get rid of a little bit of this. I should erase less. So if I have just the block, come on, work with me here. So if I have just the block, well, this is not a good place for it apparently. Okay, so I can't draw up there apparently, or I guess. So I have just the block, and I'm pulling down at some point in here. I have to worry about a couple different kinds of stress. One is the block is just looking at it is in tension, correct? I'm pulling down at the center of the block and I'm holding the top of the block up. So I need to worry. So we need to worry about normal stress. So I need to worry about normal so stress acting on. Wow, my 3D is failing me. So I need to worry about, there we go. So I need to worry about, if I was to take a section of the block, I'd have to worry about your regular old-fashioned normal stress, just trying to pull the block off of the ceiling, if you will. So there's force divided by the cross-sectional area. However, what the cross-sectional area that I care about is where that area is least. And if I move my section down the block and down the block and down the block, eventually I'll get to the point where the pin is going through. And at that point, that's all that's left of the block that's actually holding it together. So I need to reduce my cross-section area by whatever this whole takes up. So like if I have a width and a length, my area would be equal to my length times width minus the diameter of the pin. And then I have a force, I can use that area to find my normal stress. Okay? So that's the limiting case in tension then. Then I need a limiting case for shear, because the block isn't shear in different ways. So shear is when force is parallel to the face, right? So if I have my block, hey, block. Not to scale, have a force pulling down. I'm now looking at planes like this. So as I translate this through the block, where is going to be the location of the minimal cross-sectional area? Say again? Right, again, when it's in line with the pin. So if I draw this, get my section here, there's a pin somewhere in this area. That's the least area that would be resistant to shear and force. And do I want to say anything else about that? No, that's the area that's resisting to shear and force. Yeah. So now that's her area for shear. I may have written that wrong on some comments on your homework. So regard this, not what I wrote with regard to shear stuff. Okay, so that's shear. Now we have one last kind of stress that we're caring about here. Bearing stress. Remember that from the other her day. And that is, so have my block, have a pin. Bearing stress would be, what if this pin rips straight out through the bottom of the block? You're pulling on the pin. What if by pulling on the pin, you just rip that sucker right out of the block? It just pulled through all that material, which is right underneath of it. So our approximation for that, like we said in the first thing, I think, is the cross-sectional area of the material that this pin would have to travel through in order to exit the block in the direction that it's being pulled. So if I was to look at this from the bottom, so this is a bottom view, pin, it would have to go through that area of material. So that is my area now. So it's what the pin diameter wide by whatever that dimension of the block is long. And that's your bearing stress, which is just F over a different A. Does that make sense? On board with that? Any questions about that? Okay. In that case, that's all I got for today. Thanks for stopping by.